The DMAIC cycle is the backbone of Six Sigma projects. Define is like drawing a map before a road trip. You state the problem, set the project charter, identify customers' internal and external and their critical to quality needs. Think of a hospital trying to cut patient wait time. The define phase writes a clear goal. Reduce average wait from 45 to 30 minutes. Measure gathers reliable data, just as a chef would weigh ingredients before cooking. You select the right metrics, design a data collection plan, and calculate the current process performance, often using the sigma level. For example, a call center logs the number of calls answered within 20 seconds over a month. Analyze is the detective work. You examine the data for patterns, root causes, and variation sources. Tools such as Pareto charts, fishbone diagrams, or hypothesis testing are common. In the hospital case, analysis may reveal that bottlenecks occur at registration rather than at triage. Improve means you test and implement solutions. Think of trial and error like a mechanic adjusting engine timing. You use design of experiments to find the best settings, then pilot the change and measure the gain. The hospital might introduce an online pre-registration system and observe the wait time reduce. Control locks the gains in place. It is similar to putting a lock on a safe after storing valuables. You develop control plans, SPC charts, and standard operating procedures to monitor the process. Ongoing audits ensure the new registration system stays effective. Together, DMAIC provides a disciplined, data-driven path from problem identification to sustainable improvement, and it is taught in MBA programs as a project management framework that aligns operational excellence with strategic goals. Six Sigma leans heavily on statistics, turning data into insight. The Z-score measures how many standard deviations sigma, a data point x, lies from the process mean mu. Z equals x minus mu divided by sigma. A Z of 3.0 means the point is 3 sigma away, which corresponds to a defect probability of 0.27%, about 2,700 defects per million. Process capability indices assess whether a process can meet specification limits. The simple index CP assumes the process is centered and is calculated as CP equals USL minus LSL divided by 6 sigma, where USL and LSL are the upper and lower specification limits. If CP equals 1.33, the process spread fits the specification window with a 1.33 times safety margin. CPK incorporates centering. CPK equals the minimum of USL minus mu divided by 3 sigma and mu minus LSL divided by 3 sigma. A CPK of 1.33 indicates both sides of the distribution are within 3 sigma of the limits. Defects per million opportunities, DPMO, translates defects into a universal metric. DPMO equals number of defects times 1 million divided by number of units times opportunities per unit. If a widget has 2 defect types opportunities, and you find 15 defects in 5,000 units, DPMO equals 15 times 1 million divided by 5,000 times 2 equals 1,500. Control charts, for example X-bar and R-chart, plot sample means and ranges over time, with upper and lower control limits UCL and LCL set at mu plus or minus 3 sigma. Points outside these limits signal special cause variation, just as a thermometer reading above 100 degrees Fahrenheit alerts you to a fever. By monitoring the chart, managers can quickly spot drifts before they become costly defects. These statistical tools give MBA students a quantitative lens to diagnose, measure, and improve processes, turning vague quality concerns into concrete actionable numbers. Total Quality Management, TQM, is a philosophy that treats quality as a collective responsibility, not just a department's job. Its core principles can be remembered with the acronym CCEP. Customer focus: the customer, internal or external, defines what good looks like. Think of a smartphone maker that studies user reviews to decide which features to improve. The product roadmap is driven by customer needs. Continuous improvement: Kaizen, quality is never finished. Imagine a bakery that tweaks its mixing time each week to get a fluffier crumb. Each small change adds up to a better product. Employee involvement: frontline workers know the process best. A car assembly line that empowers workers to stop the line, and when they see a defect, creates a culture where every employee acts as a quality guard. Process approach treat work as a series of interconnected steps. Mapping a loan approval process highlights handoffs where errors often occur, allowing redesign for smoother flow. Elements that bring these principles to life include leadership commitment. Senior managers set the vision and allocate resources. For example, a CEO publicly commits to zero defect goals. Training and education. Employees receive tools, statistical process control, problem-solving techniques to execute quality work. Cross-functional teams. Quality circles blend perspectives from engineering, marketing, and service to solve problems holistically. Measurement and feedback. Dashboards show defect rates, cycle times, and customer satisfaction scores, enabling data-driven decisions. TQM is less about a single project and more about embedding quality into the organizational DNA. A concept MB, a learners must contrast with the project-centric Six Sigma approach. The cost of poor quality, COPQ, quantifies the hidden price a company pays when its products or services fail to meet standards. Prevention costs, money spent to stop defects before they happen. Training, process design, quality planning. Example, a software firm invests in automated code review tools. Appraisal costs, expenses to detect defects, inspections, testing, audits. Example, a food processor conducts weekly microbial testing. Internal failure costs, costs of defects found before delivery, scrap, rework, downtime. Example, a factory remachines 5% of parts due to dimensional drift. External failure costs, costs after the product reaches the customer, warranty claims, returns, lost goodwill. Example, a car manufacturer recalls 10,000 vehicles for a faulty airbag. Financial impact calculation. COPQ equals prevention plus appraisal plus internal failure plus external failure. Return on investment, ROI of quality initiatives. ROI equals open parenthesis benefit. For example, reduced COPQ minus cost of initiative close parenthesis divided by cost of initiative times 100%. If a Six Sigma project costs $200,000 and saves $600,000 in reduced scrap and warranty claims, ROI equals open parenthesis 600,000 minus 200,000 close parenthesis divided by 200,000 close parenthesis times 100 equals 200%. Understanding COPQ helps MBA students justify quality budgets in financial terms, turning quality from a soft concept into a hard-line item on the profit and loss statement. While Six Sigma and TQM both chase higher quality, they differ in purpose, scope, structure, and metrics. Objective: Six Sigma, reduce variation to a statistical target, less than or equal to 3.4 defects per million. TQM, build a culture where every employee continuously improves quality. Scope: Six Sigma, project-centric, typically 3 to 6 months, cross-functional initiatives. TQM, organization-wide, embedded in daily work, long-term mindset. Implementation structure: Six Sigma, hierarchical. Champions, master black belts, green belts, team members. TQM, flat, quality circles, cross-functional teams, steering committees, leadership sets vision. Methodology: Six Sigma, DMAIC, define, measure, analyze, improve, control, data-driven, statistical. TQM, PDCA, plan, do, check, act, iterative, often less statistical, more experiential. Metrics: Six Sigma, Sigma level, DPMO, process capability, CPK, return on investment of projects. TQM, customer satisfaction, employee engagement, overall equipment effectiveness, OEE, cost of poor quality. Change focus: Six Sigma, targeted breakthrough improvements. TQM, a continuous incremental gains. For an MBA, the key takeaway is that Six Sigma offers a tool-heavy, project-focused route to achieve dramatic performance jumps, whereas TQM provides a philosophical, organization-wide framework to sustain excellence over time. Successful deployment of Six Sigma or TQM hinges on several critical success factors, CSFS, and the avoidance of common traps. Critical success factors, CSFS. Executive sponsorship. Leaders must visibly support and allocate resources. Without a champion, projects stall. Clear goals and alignment. Objectives should tie to strategic priorities, for example, cost reduction, market share. Skilled personnel. Training black belts or quality circle facilitators ensures competence. Data infrastructure. Reliable data collection systems are essential for DMAIC analysis. Cultural readiness. Employees must feel safe to report problems, fear of blame kills improvement. Communication plan. Regular updates keep momentum and celebrate wins. Common pitfalls. Treating Six Sigma as a one-time cost-cutting tool. Ignoring the sustainability phase leads to regression. Over-reliance on tools without understanding. Using control charts without grasping variation concepts yields wrong conclusions. Neglecting the human side in TQM, focusing only on procedures without employee empowerment reduces engagement. Scope creep, trying to improve every process at once spreads resources thin. Insufficient measurement. Skipping the measure phase or using poor data makes analysis meaningless. MBA students should recognize that both methodologies succeed when technical rigor meets strong leadership and a supportive culture. They fail when either side is weak. Quality programs thrive on leadership, culture, and change management. Leaders set the tone, they model the behavior they expect, allocate budgets, and remove obstacles. A CEO who walks the shop floor and asks workers about defects demonstrates commitment. Organizational culture acts as the soil where quality seeds grow. A learning culture encourages experimentation, tolerates failure as a learning opportunity, and rewards ideas. In contrast, a punitive culture pushes problems under the rug, causing hidden defects. Change management frameworks, for example Kotter's 8-step model, are useful. Step 1. Create urgency, show cost of defects. Step 2. Form a guiding coalition, quality champions. Step 3. Develop a vision, zero defect future. Step 4. Communicate the vision, town hall meetings, newsletters. Step 5. Empower action, remove bureaucratic barriers. Step 6. Generate short-term wins, celebrate the first DMAIC project. Step 7. Consolidate gains, standardize new processes. Step 8. Anchor changes in culture, link performance bonuses to quality metrics. For Six Sigma, appointing black belt mentors and establishing project review boards provide structure. For total quality management, creating quality circles and embedding continuous improvement into performance appraisals, embed quality into everyday work. MBA learners must see that tools alone cannot drive results. Leadership must steer, culture must nurture, and change management must guide the transition. Explanation: sample MBA exam questions and answer frameworks. Question 1: explain the DMAIC methodology and illustrate how each phase would be applied to reduce patient wait times in a hospital emergency department. Define state problem, project charter, see TQS such as average wait less than or equal to 30 minutes. Measure collect data on arrival time, triage time, registration time. Calculate current sigma level. Analyze use Pareto and Fishbone to identify bottlenecks such as registration. Improve design an online pre-registration pilot. Run DOE to test options. Control implement control charts for wait time. Develop SOPs, train staff. Highlight expected ROI cost of pilot versus cost saved from reduced overtime. Question 2: derive the formula for Process Capability Index CPK and discuss its interpretation when CPK equals 0.8 for a machining operation. Show formula CPK equals the minimum of USL minus mu divided by 3 sigma, mu minus LSL divided by 3 sigma. Explain each term USL, LSL, mu, sigma. Compute example if USL equals 10.0 millimeters, LSL equals 9.0 millimeters, mu equals 9.4 millimeters, sigma equals 0.1 millimeters, then CPK equals the minimum of 10 minus 9.4 divided by 0.3, 9.4 minus 9 divided by 0.3, which is the minimum of 2.0 and 1.33 equals 1.33. For CPK equals 0.8, the process mean is too close to a specification limit or variability is high, greater than 5% defect rate, need improvement. Connect to Six Sigma target CPK greater than or equal to 1.33, approximately 3.4 defects per million opportunities. Question 3: compare and contrast Six Sigma and total quality management in terms of their approach to measurement and control. Six Sigma uses statistical measurements such as sigma level, DPMO control charts, strict control phase with statistical process control. Total quality management emphasizes broader metrics such as customer satisfaction, employee engagement, control through visual management and daily huddles. Provide a table summarizing differences and give an example of a manufacturing firm using statistical process control for Six Sigma versus a service firm using voice of customer surveys for total quality management. Question 4: A company spends $150,000 on prevention, $100,000 on appraisal, $250,000 on internal failures, and $400,000 on external failures. Calculate cost of poor quality and discuss two strategies to reduce it. Cost of poor quality equals $150,000 plus $100,000 plus $250,000 plus $400,000, which equals $900,000. Identify high-cost buckets external failures. Strategy 1: Increase prevention, such as redesigning the product to shift cost from external failures to prevention. Strategy 2: Strengthen appraisal like better testing to catch defects early, reducing external failures. Estimate potential return on investment. If prevention rises by $100,000 and external failures drop